So today's lecture is very exciting because we're going to talk about computation, which is great because this is a class in computer science. So we spent the last couple of classes a little bit motivated by that Hilbert problem, the idea of whether you could have an algorithm that could automatically check whether a statement in math or logic was valid. So we talked about the logic part, and now we want to talk about the computation, the algorithms part, and how we can mathematically define these topics. So this is what we're going to be after in today's lecture and the next lecture, and to some extent even the next lecture. Actually, by some quirk of scheduling, I'm up here again. I'm going to even be up here next time. And then, like, Professor Ada has 4 in a row, so you'll see me for a while, then him for a while. OK, and how can we mathematically define these things? So when we all have a naive or intuition about what computation is, you know, it's what you do with your computer programs. And that's a exactly correct definition and a correct intuition, but we're going to try to make things mathematically formal in the next couple of lectures. OK, so as for what is an algorithm, I wanted to put up this quote that I like. I mean, it doesn't really help us define algorithms, but I like it. I think it contains some interesting idea. An algorithm is a finite answer to an infinite number of questions. That's a lot of good points in it. This was a quotation from this person, Stephen Kleene, who is one of the founders of the theory of computation. Interesting quotation. Here's another quotation that will be a little bit inspirational for us. Although, actually, it's not so inspirational. It looks a little boring. An algorithm solves a problem if it gives the correct solution on every instance. It's more just like a fact. It's not so inspirational quotation is due to me. Well, it's not even like I had the idea. I mean, this is just the facts. But I thought if you phrase it this way, it would get across the 4 things that we want to talk about: algorithms, problems, solutions, and instances. So each of these 4 underlined words here is a technical term that we will technically define. And we're going to work, you know, for the first part of this lecture just in the last 3 terms: problem, solution, and instance, because they're not very complicated. And that'll get us set up. And we'll save the most interesting question, what exactly is an algorithm, for later. OK, so let's start with talking about what is a computational problem. And again, this is a technical term. You know, it doesn't have a wishy-washy meaning. It has a real meaning, and we're going to talk about it now, just so we have the terminology straight. So I'll kind of illustrate it with some examples, most of which I think will be familiar to you. So here's an example problem, primality. OK, and the problem here, in a nutshell, is given a number to tell if it's prime or not, as opposed to composite. OK, and with every problem, like primality, there's 2 parts to it. You have the instances, also known as the inputs, but I a little bit prefer instance, and the solutions. So a problem is composed of instances and solution pairs. And I think what the situation is with primality is kind of clear. You know, the instances are numbers, so 0 is not a prime, that's by convention maybe, and 1 is not a prime by convention. But then it gets, you know, like a proper problem. So 2, yes, it's a prime. If the input or the instance is 3, yes, that's a prime. 4, no, etc. 42, yeah, no. Phew. It's early. 251 is yes, by chance. This number is yes. This is the largest known prime in 1897. Actually, I bring it up because this is sort of a side point, but it illustrates when we're talking about primality, for example, this is a real problem that people would like to solve with their computers. They do solve it with their computers. It's a genuinely common thing that's, as we'll see in this class, used whenever you do cryptographic protocols, usually. And you should really have in your head the main interesting instances here are numbers with like 1,000 digits. Okay, and you might try to think, if you haven't thought about it before, how you can test if a number with 1,000 digits is prime. One little thing I want to emphasize is about the definition. You know, if I gave you this number and said, is it prime or not, that's a very interesting question. But that's not a problem. That's an instance of a problem. The problem is primality. So it's the entire concept. Okay, let me give you another example that was similar to a homework problem you're familiar with. Palindrome. So this is the problem of you're given a string and you want to check if it's a palindrome. Okay, that's a very nice basic programming exercise you do when you first learn how to program. So again, there's instances which are strings and solutions, yes or no. Is it a palindrome or not? In other words, is it the same as its reverse? So that's a yes. And this one is also yes. This one's pretty close, but it's a no because of that extra s on the end. This is a yes. This random string is no. This is also some random string, but if you stare at it closely enough, the answer is yes. Okay, etc. Okay, so you get the concept. Palindrome is got some instances which are strings and yes or no solutions. Now, these first two examples that I've talked about, primes and palindromes, are actually kind of a special case of problems. They're what's called decision problems. That's also a technical term, decision problem. That just means a problem where the answer is yes or no, where the solution is yes or no. Okay, and there's many different conventions people use for decision problems, whether you call it yes, no, or true, false, or 1, 0, or accept, reject. It's all the same, and actually I might use one or the other here, but a decision problem just means there's a binary answer, true or false, yes or no. Okay, but I mean, of course, there's lots of computational tasks that you like to do that have more than just a yes or no answer. They have some output, and that's perfectly fine. I'll show you a couple of very simple examples. Multiplication. And again, you usually think of this as pretty simple, but you should imagine in your head, the algorithm maybe for multiplying two 1,000-digit numbers. Okay, so here the instances are pairs of numbers, and the solution is also a number. 50 times 610 is 30,500, whatever. Okay, or another, very, very classical computer science problem is sorting. Here the input is a list, maybe of strings, and the solution should be the same list, but in sorted order. Okay, so to summarize, a problem is a collection of instances and their associated solutions. Okay, and usually, there's some theme to them, like palindromes or multiplication. Okay, so the problem is the instances together with the solutions. Any questions? Okay. Great, so let's talk a little bit about representing problems. We're going to do it mathematically, but we're also a little bit inspired by the fact that ultimately we're going to be solving these with computers. So as you saw in these previous examples, there's a wide, wide world out there of computational problems. Many, many things you'd want to solve with an algorithm, and the instances can be numbers, like in primality, or strings, as in palindromes, pairs of numbers, lists of strings. The input could be a graph or an image. Many, many, many different possibilities. Okay, and if we're going to reason about these things mathematically, we kind of have to tame this situation a little bit. So this is the most standard way to do it. As you know, all of these kinds of objects can be encoded by strings. Okay, if you think about it, let's say on today's real-world computers, when you have these objects stored on your computer, really it's somewhere in memory. It's like a sequence of bytes, maybe. And a sequence of bytes is really like a string, where each character, can be between 0 and 255 or something. And you could even also think of it as a sequence of bits, right? I mean, a byte is 8 bits. So as you probably are familiar, kind of any object, you can really encode it in some natural and convenient way, usually with binary strings. Especially if it's numbers, you can write them in binary. If it's strings, maybe you have a little mapping that converts each letter to 5 bits or something. Okay? So almost always when we talk about problems, we imagine that the instances are strings. So while I'm on the subject of strings, let me remind you or tell you about a little bit of string notation, because it's actually going to come up quite a bit in this lecture. So we first have this term alphabet, which means a finite set of symbols. Usually we write it sigma, and that just means what the characters are. So the alphabet 0 and 1 is a pretty popular choice, binary strings. It could be like, the 26 letters of the alphabet, or the Latin alphabet, let's say, or the byte values between 0 and 255, so a finite set of symbols. A string means a finite sequence of symbols. And we definitely allow the string of length 0. It's a little bit funny, but that's the empty string. And in theoretical computer science, it's usually written epsilon. You might have think of it as like double quotes. But the length 0 string exists, and it's denoted epsilon. Sigma to the n means all the strings of length n with symbols from sigma. And sigma star means just all the strings of any length, finite length. Okay, and finally, we have one more term you might not know so well, language. That's just any collection of strings. So in other words, it's a subset, L, of all the strings. Okay, let's go back to representing problems. So we kind of decided, I hope you're okay with the fact, that we can encode instances of problems with strings. Okay, and so we can really think of a problem which has, a bunch of instances and the corresponding solution, which could also be encoded as a string, as a function, f, that takes strings to strings. Okay, that maps the instances to the solutions. That's really what a problem is. And the special case of a decision problem, where the solution is either yes or no, can be thought of as a function that maps strings to no or yes, depending on whether the string really is a yes instance, a yes solution for the problem. Okay, or we could put 0 and 1 here, or what have you. So I want to focus a little bit on decision problems, because it's kind of the simplest case of a problem. And I think, as we'll see later, it's almost without loss of generality to only worry about decision problems, yes or no problems. Because there's also another way to look at decision problems. That's why I want to spend a little time on it. So a decision problem, if you think about it, is really equivalent concept to a language. So one way you can think of a decision problem, F, as a language, is you can let the language L just be all the strings whose correct solution is yes. Okay, and conversely, if you have a language, you can think of that as a decision problem. The problem is, given an input string, is it in the language, yes or no? Okay, so this is an important concept, and we're going to use both of these ways of looking at a decision problem, as a function, mapping strings to yes or no, or as a language, just a subset of the strings that are the yes strings. Okay, so before we kind of talked about palindromes as a decision problem mapping a string to the yes or no answer, but you can also think of it as a language, just a language of all strings that equal their reverse. Okay. Any questions about this? Okay, good. So that's mostly what I want to say about problems and solutions and instances. So now we kind of know what we're up against, the things that we're trying to solve with computer algorithms. And we want to get into now the trickier question of what is computation, or what is an algorithm. Now, we're not going to really fully answer that question in this lecture. In this lecture, we're going to sort of warm up by discussing a very, very, very simple kind of computing mechanism called deterministic finite automata. This is the plural of the word automaton, which means machine. So this kind of computational model is really wimpy. It can only implement really extremely restricted kinds of algorithms. There's like lots of really simple computational problems that it cannot solve. So why do we study this wimpy concept? Well, a couple of reasons. It has some interesting applications, and for the things that it can solve, it kind of does them in a really good, efficient, cool way. So that's nice. And it's really a good warm-up before we really dive into the full definition, full-blown models of computation. This kind of very simple model is really a good warm-up to help us get accustomed to the idea of mathematically defining computation. So for the rest of the lecture, I'm going to talk about this concept, deterministic finite automata. Okay, so they're also called DFAs. I might start calling them DFAs. So I'll again try to define them or explain them with some pictures, with examples. So a DFA is a computing machine that deals with inputs over some strings over some alphabet, maybe 0 and 1 in this example. And it looks like this. So that's, if you haven't seen this kind of picture before, it looks a little crazy. So I'm going to explain like every part of what's going on in this diagram. This is kind of like the diagram of a machine, a DFA machine. Okay, so these circles, there's 4 of them here. This one, this one, this one, and this one. They're called states of the machine, kind of the state it can be in. And these arrows, you see there's arrows between the states labeled by the symbols. Those are called transitions. We'll kind of see how it all works through an example now. So it's a computing mechanism that tries to decide if a given input string is in some language. So it's going to try to look at this string and output either yes or no. So here's an input string, for example, 0, 1, 1, 1. So how does it work? Well, the machine starts in one state called the initial state. And which state is that? There will always be, in this diagram, a little arrow coming from nowhere and going to a state. So that's this one, and that tells you what is the initial state. It's this circle. Okay, and what you imagine happens is you start in this state, and you have this string 0, 1, 1, 1. And what happens at every step is, when you're in this state, you look at the first symbol in the string. In this case, it's 0, and you follow the arrow labeled by that symbol. So here, if it was 1, you would have gone here, but it's 0, so you're going to follow this loop. Okay, so you do that because the first character is 0, and then you're finished with the 0, you delete it. So what you're left with is the string 1, 1, 1, and now you repeat. So we got 1, 1, 1. We look at the first symbol, it's 1. So we follow the arrow labeled 1. Zoop, it goes up here, and it deletes that first character, which was 1. Okay, we keep going. The first character is 1. Here, both of the outcoming arrows 0 and 1 are the same. So we follow this one. We have a new first character, which is again 1. So we're going to follow the arrow labeled 1, which is a loop. We come back here. And now we're down to the empty string. We ate up all the characters. So this is the empty string, and that's when the computation stops. When you get down to the empty string, you've read all the characters. Okay? And now you can think of whether the machine says yes or no, or accept or reject, as depending what state it's in at the end. And here's where the difference between the single circle and the double circle comes in. We say that the machine accepts the input or says yes to the input if the process ends in a double circle. So like the double circles are the accepting states. And otherwise, we say it rejects the input if it ends in one of these single circle states. Okay, we're going to talk more about this, but any initial questions about this somewhat complicated notion? Yeah?
Wait, so would the language be the set of all strings that map only to the double circles?
Exactly. So you can think of, as we'll see in a second, you can think of this machine as deciding a language. It sort of says yes to all the strings that make it end up in a double circle. So that's kind of how it operates and what language or decision problem it solves. We'll say this a bit more precisely later. Any more questions? Okay, so let's go over it a little bit more carefully. So this is our example DFA, and we'll look at its anatomy. I mentioned it mostly, but I'll remind you. Has these circles called states, and we usually label them by letters or words or some such thing. There's always one start state, and in the picture you draw an arrow to indicate which one it is. Again, the accepting states are drawn with double circles, and the rejecting states are just single circles. And that doesn't affect things at all as it's going along. It only affects like the final decision at the end, where you end up. And the arrows are called the transition rules. Okay, so for every state, you need to have one arrow coming out of it to another state, potentially itself, for each symbol in the alphabet. So here the alphabet is 0, 1, so every state has a 0 arrow coming out and a 1 arrow coming out. Collectively, those arrows are called the transition rules. Okay, so let's talk about how this question, how you can think of DFAs as computing mechanisms. So let's say M is a DFA. Okay, M usually is the letter you use, it stands for machine. And let's say it uses the alphabet sigma, so it expects its input words to be strings using the alphabet sigma. We think of it as a computing mechanism which accepts some of the possible input strings and rejects the rest of the strings. And so we can define, given a machine, the language of all strings that it accepts. That's all the strings that force it into an accepting state at the end, and that has the notation L of M. And sometimes we call that the language accepted by M or the language decided by M. Those are synonyms. Or you can also think of M as trying to solve a decision problem. If P is some decision problem, a mapping from strings to yes or no, or equivalently accept, reject, we say M solves it if L of M is exactly P. Okay, so I've given you some definitions, and now let's explore it a little bit. So what language does this DFA decide? We've got a very quick hand up there. I'll ask you in a second. Okay, so just to warm you up, it uses the symbols 0 and 1, and the string would start here. And if you see some zeros, you stay here. But if you see a 1, you would go over here, and the zeros keep you here. But if you see a 1, you come back. So, yeah, can you say what strings are accepted?
So it's any string with an even number of ones.
Yeah, that's exactly right. It's any string with an even number of ones. Because as you're reading the string's characters, as long as you stay at 0, you stay in this state. And you can kind of think of this state as, so far I've seen an even number of ones. Okay, and so when it sees a 1, it goes over to this state, which you can think of as, so far I've seen an odd number of ones. As long as you see a 0, as you're reading from left to right, you stay the same. And if you see another 1, you go back to the even state. And you accept, this is the accepting state when you've seen an even number, and this is the rejecting state. Any questions about this? Okay, how about this machine? It's even a little bit simpler. Somebody say what language it decides? Okay, good. I see a lot of hands. That's good. I think you had your hand up for a while.
All strings that have an even length?
Yeah, this one's even a little bit simpler. It's all the strings that just have an even length, an even number of characters. Because you see, you start in this state, and, well, every time you read a symbol, you go over here, and then the next step you come back, so you just keep going back and forth. And the string ends up getting accepted if it had an even number of characters. Okay, so this is actually why I kind of like DFAs. They're a little bit fun, right? They're kind of wimpy computing devices, but it's a little bit fun to see what they do and how you can construct them. Okay, this one's a bit weirder. Here, just for fun, I made a DFA that works on strings with 3 letters, A, B, and C. And here it is. So what language does this one accept? You answered one. I'll come back to you later. Actually, let me slow down. What is one string that this machine accepts? Just name one string that this machine accepts. You want to say? A, yes, that's right. So this is the start state. If the whole string is just A, you would pop over here, and then it would be done, and you'd accept. Somebody say another string that it accepts? B, yeah. How about another string that it accepts? Yeah, C, C. Another one? How'd you guys all know to say CC first, and then CB? Well, anyway. C, B. And another one? Oh, it must be it then, right? That is it, yeah. This is I don't know. this is just like weird language I made up. There's nothing interesting about it. And you can kind of see that's it, right? Because somehow all the arrows are going to the right here. As you read more and more characters, you can kind of see you keep going to the right. And basically, if you read any string other than this, you'll eventually get to, well, if it's longer than this, you'll get to this Q3. And Q3 is kind of a dead state, right? Once you get to Q3, no matter what you read, you just keep hanging out in Q3, and you're eventually going to accept. So I think with a little bit of thought, you can convince yourself that it accepts exactly these 4 strings. Yeah?
Is it possible to have 2 outputs from a single node with the same character?
Very interesting question. Can you have 2 arrows coming out of a single node with the same character? Well, what do you think would happen then? The answer is no, it's not allowed, but maybe you could allow it. What do you think should happen? Oh, that's a very good idea. The suggestion was that maybe with probability half it follows one, and probability half it follows another. You could invent such a concept, and in fact, it has been invented. It's like a probabilistic version of DFAs. It's quite interesting. Maybe we'll make a homework problem about it. Actually, we have a homework problem about what would happen if you add this non-standard feature to have 2 arrows with the same character coming out of the same state. So you'll get to explore just this starting an hour and a half from now. That should have been like, not ah. Okay. How about this one? You guys are very fast. How did you, wait, you're a TA. You cannot put up your, well, you can if you want, but yeah, no, I see him. I just wanted to give everybody a little chance, but thank you, yeah?
The empty string and all strings ending with 0.
Oh my God, have you, that's right. It's all strings ending with 0. Because you see what happens here is you come in, maybe you see some zeros, you hang out, and then if you see a 1, you go hang out over here in a rejecting state, and you're not going to accept unless you see another 0. So you see you only accept, well, it looks like you have to end with a 0 in order to accept. You have a comment?
Don't you have to union epsilon?
Yes, in fact, the person already said this correctly. There's a little trick, which illustrates that you have to be quite careful when doing these. It's not actually just these strings, because it would also accept the empty string. So never forget the empty string. If the string has no letters, then it just starts and ends right here, and the initial state is an accepting state. So the empty string doesn't really end in a 0, so you have to include it separately. Okay, so this is just a little warning to you to always be thinking about the edge cases, which this person was very sharp on the edge cases. Any questions? Is that a question or no? Okay, now at this point I would like to actually make a very formal mathematical definition of DFAs. Now on one hand, I hope you've kind of got the gist of it already and you know what we're talking about. But I want to give a very formal mathematical definition for a couple of reasons. One, having some notations can really help you reason about them mathematically. And ultimately, the reason we want to do this is so that we can really prove super rigorous proofs about DFAs if we wanted to. And that's what this is saying. It illustrates that we could really formalize completely rigorously this notion of computation. Now, to be honest, we're not going to ultimately dwell upon this mathematical formalism too much in the class because, what I explained before is pretty good. I think you got the gist, but just to show you how you can do it. Okay, so a deterministic finite automaton, if you really want to think about it mathematically, you can think of it as a 5-tuple of objects. It's like it comes with 5 components, and there are Q, sigma, delta, Q0, and F. And that really describes the whole finite automaton. And we'll go through what each of these pieces is precisely. So Q is a set, and it's a set of states. Okay, and it should be a non-empty finite set. So in the very first example that we talked about, there were 4 states, so Q would be some set with 4 elements. Sigma is the alphabet that it operates on. This we've sort of talked about already. Delta is the transition function. This is the most complicated part. Delta is a function that encapsulates all the arrows. So what does an arrow really have to do? It has to tell you for each state that you could be in and each symbol that you could be reading, what state you would go to next. So really it's a mapping or a function from a pair, a state and a symbol, to another state. So this, if you're in this state and you're reading this symbol, what new state do you go to? I'll give you an example soon. Q0 is pretty simple. It's just any element of the set of all states, and it represents the start state. And F is a subset of states, standing for all the accepting states. Okay, so all these mathematical objects put together totally define the DFA. Another reason why I wanted to show this definition is you could actually, if you're a very sophisticated person or you really like to play with DFAs, you might write a computer program whose input is a DFA. You might want to write a computer program in Python or whatever that took in a DFA and simulated it. That'd be like a fun thing to do. And you would need some way to write down what is the DFA, right, as the input. It's hard to really pass these funny pictures into your program, right? So you need to encode it in some way with strings, and this is really how you do it. You do an encoding of what is the set of states, an encoding of what the alphabet is. This would be some list of states, some list of symbols. Maybe you'd have some table or array for what delta is, etc. Okay, so this kind of illustrates that it's really just a mathematical object which itself could be encoded with strings. Okay, so let me give an example of how all this works with our favorite starting DFA. So here Q is a set of size 4 that contains the states, Q0, Q1, Q2, Q3. Sigma, the alphabet is 0 and 1. Delta, we'll come back to. Q0 is the starting state. And what is F? Yeah? It's the set Q1 and Q2. It's a subset of Q. Okay, and what is this delta? So remember, delta is a function that takes in a state and a symbol and tells you what state you would go to next if you're at that state and saw that symbol. And you could write it out as a table like this. So here's the table here. This is saying delta of Q1 and 1 is Q2, which is like saying if you're in state Q1 and you read a 1, then you go to Q2. Okay, or if you're in state Q0 and you read a 0, you go to state Q0. Any question about this? Okay, so I want to have one more technical slide. So we talked about how to really mathematically formalize what is a DFA. There's one more step, though. How can you formalize what is DFA computation? So we also had this story about what happens when you give a string into a DFA. It goes around the states, and it eventually accepts or rejects. That was pretty precise, and I think it's okay. But if you really want to mathematically formalize it, to reason about it, here's how you could do it. So let's say we have some string W with n characters, W1, W2, W3, up to Wn, and a natural number. We can define the concept that M accepts this string if, well, we want to say that it passes through a succession of states. So we would say there exist states R0, R1, R2, up to Rn, all in the set of states Q, such that there's going to be 3 conditions. Can somebody say what these conditions should be? What do we want to say to really encapsulate that the machine accepts the string? Anybody that has not answered a question before? I'll give you the first one, and then maybe you can tell me the next 2. Oh, okay. Go ahead.
Delta of R sub I, comma W sub I equals R I sub R equals R of I sub 1.
Yeah, this is the most complicated part. You want to say the following 3 things. You named the middle one. You want to just say that R0 is the initial state. This I'll come back to in a second, but it says that, each state R, well, I'll say it now. This says that for each sort of time step, 1, 2, 3, 4, if you're at some state R at time t minus 1, and the tth character is w, then rt should be what you get out of the transition rule. It should say that rt is the next state you would go to if you were in state rt minus 1, and you're reading the character wt. And finally, the last state, rn, should be in the set of accepting states. Okay, and otherwise we say it rejects, and really this just says that this sequence of states, R0, R1, up to Rn, is like the computation trace of the machine on the input W. It says all the succession of states that the machine hits starts at the start state, and this encapsulates that it's following the correct sequence of states, given the word. Mm-hmm.
Is there any notion of like equivalent DFAs? Because, I mean, it'd be easy to like make two that compute the same problem but have different like structures. Is there a formal definition?
That sounds like a good definition. Yeah. So the question was about equivalent DFAs, and it raises a very good point, which is that you can build two different looking DFAs that compute the exact same thing, just as in normal life, right? I mean, you can write two different computer programs that have the same input-output behavior. Same is true of DFAs, and indeed you can say that two DFAs are equivalent if they have the same language. Okay, so actually these are all languages that you can make a DFA to decide. So here's a simple one, just these two strings. This one is all the strings except for those two strings. You know, these are a bunch of interesting languages. And you know, you can go home after this lecture and go to your dorm room and try to make a DFA for all of these languages. It's kind of like fun little programming problems when you're programming in this weird language of DFAs. Or I have office hours right after this. You should come to them. We'll kick back, draw some DFA diagrams on the board, solve some of these problems. It'll be good times. Okay. So those are all some interesting examples of decision problems or languages that you can solve with DFAs. So in fact, there's a technical term for languages that can be solved by DFAs, and that's the term regular. You say a language is regular if there's some DFA which decides it. I don't know why they called it regular, but that's what they called it, regular language. So here's a couple of questions about regular languages that will occupy us for a little while. Question 1, are all languages regular? And question 2, what's another way? Are there any other ways to tell or prove that a language is regular except by drawing a DFA and proving that it works? Okay, well let's start with this one. Are all languages regular? This is a bit, you have a question, or are you going to answer this question, or?
No, I have a question.
Yeah.
Does a language permit infinite strings?
Good question. Does a language permit infinite strings? No. So for us, a string has to be finite. And so therefore, a language is a collection of strings, is only finite strings. Now, that's a convention. That's going to be our convention. You can mathematically talk about infinite strings if you want. It might, in fact, even come up in a couple of lectures. We'll see. You could talk about it. It's actually even interesting to think about DFAs operating on infinite strings, but we won't. For us, a string will be finite length. Okay, so coming back to this question, are all languages regular? I think a lot of people were shaking their heads. I mean, that would be a bold claim. I mean, it's saying that you can solve any decision problem with these little DFAs. That doesn't seem too plausible, and in fact, it's not the case. So here is a theorem that I want to spend some time on. It gives an example of a language that's provably not regular. Provably cannot be solved by a DFA. Okay, this is the most sort of famous language that cannot be solved by a DFA. It's called 0 to the n, 1 to the n. And actually, to even explain what that means, I have to give you one little bit of notation. I wrote that here. So if s is a symbol and n is a natural number, s to the n is a shorthand for the string of length n, which is all s's. Okay, so s to the 3 means the string SSS, s to the 5 means SSSSS, S to the 1 means S. S to the 0 means empty set, etc. Okay, so the language that we're going to study for a while is the language of all strings of the form 0 to the n, 1 to the n for some natural numbers. So in other words, it's exactly this set. You know, it has all the strings that have some number of zeros and then the same number of ones. Okay, and that number of zeros and ones could also be 0 if you want. So this is a language, or if you want to think of it as a decision problem, it's like a computer program problem. I give you a string of zeros and ones. You have to tell if it's a bunch of zeros and then the same number of ones. That's actually a very easy problem to solve, right? I strongly imagine that you could all solve this problem in your favorite programming language quite quickly. Unless your favorite programming language is DFAs, because you cannot do it, as we'll see. And so it actually illustrates that something I said before. DFAs are kind of a really wimpy model of computation. They can't even do this. Okay? But this is a nice theorem because it's kind of interesting to somehow show a negative result, that like this kind of computational model cannot solve this problem. Yeah? The question is, can you construct a DFA with only one state? Yeah, you can. That's allowed. Trouble is, a DFA with only one state, what kind of languages would it decide? Yeah, well, there's two different languages you could do with one state. The language that contains everything or the language that contains nothing. Because that state has either got to be accept or reject. And you're just going to always hang out in that state. So it'll either accept everything or reject everything. That's a good question. Yep.
In my computer, is there an n that's not computable?
Pardon me?
In my computer, don't we have an n that's not computable? Like, want to run out of memory at some point?
In your computer? Ah, okay, that's a good question. Well, yeah, the question was, if you went home, I think, if I understand it, if you went home with your favorite programming language, maybe arguably you could not solve this problem because, I mean, if n is 2 to the power of 1 trillion, then your computer probably couldn't even represent the input. Okay, that's kind of a valid point. We'll actually talk about that point in the next class. Okay, but so, yeah, so these DFAs in some sense are kind of theoretical because they can process strings of any finite length, including unimaginably large lengths. Okay, so we want to prove this theorem to prove that it's not a regular language. So it's a bit tricky. We have to show that DFAs cannot solve it. Or in other words, for every DFA M does not correctly decide this language. Now, what is the intuition here? Imagine you're going to try to do it. So for the DFA, which kind of reads the characters from left to right, if it's going to decide this language, it kind of seems that like as it's going along the zeros, it sort of needs to like remember how many zeros it's seen, because if it hits the ones, it's got to sort of check that it had equally many ones. But it's hard to remember that because n could be sort of any number, but a DFA only has a finitely many states, only a sort of a finite amount of memory. So it seems like it's going to be hard for it to handle arbitrary n. Now that's a correct intuition. It's not a proof. I mean, it's not a rigorous proof, but it has some of the ideas. But it's also important to really give a proper proof. Maybe this looks convincing to you, but I think you should check yourself because you could have similar intuition about a false statement. So this is a little side note you can think about. Here's a similar looking language, the set of all strings where the number of substrings 1, 0 is the same as the number of substrings 0, 1. That also looks like you could apply the same intuition to it. But it turns out this one you can solve with the DFA. I'll let you think about that in the privacy of your dorm room. But in any case, this intuition is correct, and let's now try to turn it into a proof. So let's not jump straight into the proof. I want to try to explain how you might kind of construct this proof yourself. So one thing we have to do, we have to show that every single DFA does not decide this language. So let's not go straight there. Let's kind of warm up. Let's try to show that there's no DFA with 7 states that decides this language. Okay, I just picked 7 sort of randomly. We definitely have to show at least this. So let's try to show it. So, okay, we have to say, suppose there were a DFA with 7 states that decides this language, and come to a contradiction. So let's say this is our DFA with 7 states. Now you might say, wait a minute, you didn't draw the arrows, you didn't draw what's accepting. Yeah, I didn't, because actually there is no DFA with 7 states that accepts this string. So any picture I would have drawn would be wrong. So let's just kind of keep it hazy in our heads, like supposedly there's for contradiction, supposedly there's some DFA with 7 states. I kind of half drew it, so like a hazy picture in my head that what it might look like. So I call the states Q0 up to Q6. So now, here's another kind of a thought experiment. Let's kind of imagine sort of what could happen if I gave it this input. This is a tricky input. Is this input in the language or not in the language? It's hard, right? You kind of squinted like, I don't know. I don't even know. I think it is, but it's a little bit hard. Okay. Some people are very good at discerning symbols with their eyes. Okay, so let's imagine kind of what happens when this DFA, hypothetical DFA, reads this input. Okay, so it starts in the initial state, and it reads a 0. So then it goes to some other state, I don't know, hypothetically Q3. And then it does another 0, and it goes to maybe Q4. It reads another 0, it goes to Q6. I'm just making this up. It reads another 0, and it goes to Q2. Reads another 0, maybe it goes to Q1. You would fast forward this part if you were watching the video later. Reads another 0 and goes to Q5. Maybe it reads another 0 and goes to Q4. Wait a minute. We were in Q4 before. I don't know if you remember, but in this hypothetical picture, we got to Q4 after 2 zeros. And then we got to Q4 again in this hypothetical picture after 7 zeros. So that's a little bit funny because it says the DFA can't really tell the difference in some sense between starting with 2 zeros and starting with 7 zeros. I mean, both of these strings lead you to Q4. And at that point, anything you do in the future, it doesn't remember how you got here. It doesn't remember kind of if it's 2 zeros or 7 zeros. It's going to do the same thing. So actually, forget this input. Like, on one hand, if you do 7 zeros, maybe you get to the state Q4 in this hypothetical example. If the rest of the input, let's say, was 1, 1, 1, 1, 1, 1, 1, then you go around some more, and you'd better come to an accept state, because 7 zeros followed by 7 ones is in the language. But that's a problem, because in this hypothetical DFA, you also get to this state if you do 2 zeros. But then, if you do 7 more ones, you actually better come to a reject state, right? Because 2 zeros followed by 7 ones is not in the language. And that's the contradiction. It says, if it really happens like this, that you get to Q4 after 2 zeros and after 7 zeros, then it can't possibly be correctly deciding this language. Indeed, yeah. So now that was, kind of a weird, hazy example. But what was the key part of that example? The key part was kind of that you had 2 different length strings of zeros that took you to the same state. And actually, something like that is always going to happen for any DFA, even if it has 100 states. Can somebody say why? Yeah?
Because for each number of states, you can always come up with an end that is larger than that.
Yeah. Whatever the number of states is, if you look at like a bunch of zeros that's more than that number, then, there's a famous little principle that you can apply. Does anybody know it or want to say it out loud? Yeah, the pigeonhole principle. It's a very simple use of it. So here's a full proof. Like I think I write like a totally full, correct proof that this language is not regular. Suppose, for a contradiction, that you had some DFA M that decides this language. And let's say it has some number of states, k. Let Ri be the state that M gets into after it processes I zeros in a row. It's got to go somewhere after I zeros in a row. Let's call that state Ri. Now look at all these states, R0, R1, R2 up to Rk. That's k plus 1 states. But there's only k different states in the machine. So by pigeonhole principle, there has to be a repeat in this list. That's like the Q4 we saw hypothetically last time. OK, so let's just give a name to that. Let's say that Rs equals Rt, where S and T are different times, if you will, or indices, between 0 and k. Now, we're going to start to use the fact that M supposedly decides this language. Well, if you look at the string s many zeros followed by s many ones, that's in the language. You're supposed to accept that. So this machine gets to the state rs after reading s many zeros. Then it's going to process s many ones. So that better take it to an accepting state. But now look at this string, t many zeros followed by s many ones. So when m processes this, it reads t many zeros and it gets to the state rt by definition. Rt is the same as rs. So it gets to the state rs. Then it processes 1s. And we just saw up here that if you're in state rs and you process 1 to the s, you get to an accepting state. But that's the contradiction. 0 to the t, 1 to the s, t0s and 1s's, s1s is not in the language because s differs from t. So this is a contradiction. Yeah?
If you were to put like an upper bound on it, so it couldn't go above some k,
Yeah?
is this language regular then?
Yeah, the question is, what if the language, instead of n many zeros followed by n many ones for any n, was, let's say, n many zeros followed by n many ones for any n that's up to 1,000? And could you build a DFA that accepts that language? Any guesses?
Yeah. Yes.
Yeah, you can. I'll let you think about it. In fact, any finite language, any language that has only finitely different many strings in it, can be decided by a DFA. It's regular. That problem was almost on the homework, but we rejected it. Okay. However, on the homework, you will be required to prove that some other languages are not regular. And I will tell you that most of the time, the proofs are very similar to this template. So it's worthwhile to study this template. It usually goes like this. Not always, usually. You have some language you want to show it's not regular. Assume for contradiction that there is some DFA, M, that decides it. M has some fixed number of states. Then you usually argue by the pigeonhole principle that there's some strings x and y which reach the same state. And this is where you have to be kind of creative to figure out what kinds of strings x and y you want to look at. And then the final piece of the puzzle will be to show that there's some string z such that xz is in the language but yz is not in the language. And that's a contradiction because if x and y get to the same state and then they both process z, they're going to come to the same decision. Yep.
You just said that finite languages are always regular. So if we draw an automaton that looks like a tree, does that always work?
Yeah, you could have solved this hypothetical problem on the homework. Yeah, a good solution for that, for proving that, is to have a DFA that looks like a tree. Okay, so we talked about whether all languages are regular. In fact, there's not true. There's lots of non-regular languages. What about some other ways to tell if a language is regular? Here's another theorem I want to show to you called the union theorem. And this is a definition. It's really a definition you already know. It's just the definition of union, but we'll apply it to languages. If L1 and L2 are languages, sets of strings, L1 union L2 is another language. It's all the strings that belong to at least one of the two languages. And the union theorem, which we'll talk about now, says that if L1 and L2 are both regular, then so is L1 union L2. So if a DFA can check belonging to L1, and there's another DFA that can check belonging to L2, there's a third DFA that can check the OR of these two conditions. So let's give an example. We're going to also prove this theorem. So let's say L1 is the strings with an even number of ones. We did this one. There's a DFA for that. It's this one. I drew it sideways. And let's let L2 be all the strings with length divisible by 3. So we didn't quite do that one, but it's not too hard. It's this one. You see, it's just like a little cycle of length 3. You pop around the states in a circle no matter what you read. That's the DFA for it. So now L1 union L2 is another language. It's kind of a weird language. It's all the strings that either have an even number of ones, or they have length divisible by 3, or both. And the union theorem, which we're kind of trying to illustrate the proof of now, claims that there's some DFA that checks that condition. So I'm going to show you a picture here, which I hope will kind of illustrate the idea. Let's say we had an input like this, and we want to tell if it's in the union of the languages or not. So is this one going to be in the union of the languages? Yes, because it has an odd number of 1s, so it's not in L1, but it has length 6, which is divisible by 3, so it's in L2. So it's in the union. Now let's just kind of watch what happens to both these automata as they process this string. You know, they start at the beginning, and then they read 1, so this one goes over here. This one's just going to always tick along. 0, 1, 0, 0, 1. And in the end, now that we're done, it's sort of as expected, right? This one ended in a rejecting state because it had an odd number of 1s. This one ended in an accepted state because the length was a multiple of 3. So how could we build a DFA that solved the union? Any ideas? Yeah?
Have each state in your new DFA correspond to a pair of states from the old DFA?
Yeah, great. And kind of make it follow both rules simultaneously, right? And in the new DFA, which state should I mark as accept and which should be a reject?
It's accept in either of the two original DFAs?
Exactly. Exactly. So I'll go through that idea. It's exactly right. So we're going to try to make a DFA that keeps track of both states at once. Okay, so how many states will this new DFA have? Shout it out. 6. You need 1 for each pair of states here, so 2 times 3. So it's going to look like this. Sorry for the crazy diagram. 6 states, and each one corresponds to a pair. This is like all the Q even, comma, a P state, and this is Q odd, comma, a P state. So kind of the rows tell you whether you have an even or odd number of 1s, and the columns tell you whether the length is congruent to 0, 1, or 2 mod 3. Okay, and I put in all the arrows to transition, I think, in the right way. So like if you have an even number of 1s, and your length is congruent to 0 mod 3, and you see a 1, then you have an odd number of 1s, and your length is congruent to 1 mod 3. Okay, so if this is the input, you start here. You see the 1, so indeed you come down to here. It's always going to sort of tick around horizontally for each step, and it goes back and forth, up and down, whenever you see a 1. Okay, so it stays down here, comes back around to here, to here, to here, to here. So at the end, we got into this state, which is right. You know, it records if you have an even and odd number of 1s, and also it sort of knows if your length was congruent to 0 mod 3. And as suggested, we want to make the final state accepting if either of the sort of component parts of the state was accepting before. Okay, so this is mostly what a formal proof would look like, depending on how much information you want to put in the last step. So formally, if L1 is decided by this automaton, M1, L2 is decided by this other automaton, M2, which has all the same components with the prime, except that they have the same alphabet. Remember, this is the states, the alphabet, the transition rule, the initial state, and the accepting states. Then the DFA for the union has 1 state for each pair of M1 and M2 states, the same alphabet. Come back to the transition rule. You start in the state that corresponds to the 2 initial states, and the accepting states are all the states where one of the 2 initial base states is accepting. And this is the formalism for saying that the transitional rule kind of just does the 2 old transition rules simultaneously. Okay, and in some sense, if you think about it for a while, you'll see that this works. You might want to fill in some more details if you were writing this properly, but this is how the formal proof would look. Okay, I want to tell you, that's the end of the union theorem. Any questions about it, by the way? Okay, I want to tell you 2 similar, but somewhat trickier theorems. So we just saw this one, that if L1 and L2 are regular languages, then so is their union. Okay, now here's another operation on languages. If L1 and L2 are languages, we say their concatenation is another language. It's the language of all strings that look like some string x from the first language followed by some string y from the second language. Anything you can get by gluing together a string from L1 followed by a string from L2. And it's a theorem that if L1 and L2 are regular languages, then so is this concatenation. Here's another one. This is another funny operation called the star operation, invented by Stephen Kleene, our inspirational character from the beginning of the lecture. If L is a language, then L star is another language. It's a bit similar. It's the set of all strings that you can get by putting together 0 or more copies of strings from L in a row. So you can put together they can be different strings from L. If you take any bunch of strings from L and concatenate them all together, that's a string in L star. Okay, and it's also a theorem that if L is a regular language, then so is L star. Okay, so these are the three theorems I just told you about. This one, the union theorem, we proved. These ones we didn't prove. And in fact, they're somewhat trickier to prove. But you're going to prove them on your homework. Okay, so these are very fun theorems to prove. So let's pretend you've done your homework. And we now know these three theorems. Now actually, there's something interesting about these three theorems. They might remind you of something that we did in lecture 2. They kind of look like, anybody guess what I'm thinking? Yeah, they kind of look like deduction rules. You know, like if you kind of have L1 and L2, then you can get like this thing. And indeed, you could make a nice deductive system using these rules. So this is a deductive system for regular languages. This one's a bit kind of awesome because the objects here are languages. They're not strings, they're languages, sets of strings. So the initial objects in this deductive system are languages. They're extremely simple languages. The empty language that has no strings, that is a regular language, right? You could just have a one-state, we talked about it, a one-state automaton, which was a rejecting state. And also the language that has just one string, and that string is just one character long, those are also regular languages. We mentioned before that actually any language with only a finite number of strings is regular, but these are really particularly simple regular languages. So those are some regular languages. And these theorems we saw give us, sound deduction rules, that if you can get L1 and L2, you can deduce their union, or their concatenation, or the star of one of them. Okay, and we know from the previous slide, these theorems, we proved this one, that any language you can deduce in this system is regular. Of course, I think that may lead you to ask a natural question about the reverse, the converse. Namely, is it true that for every regular language you can deduce it in this system? Turns out the answer is yes. That's like a very cool fact. Every regular language over a fixed alphabet you can get in this way by combining these super simple languages, empty and single letter languages, and these union, concatenation, and star rules. So if you have some DFA that decides a language L, you can deduce it from this system. That fact is also a little tricky to prove. It's not on the homework. But it's true. It's a cool fact. And in fact, it's related to a concept that maybe you've even seen before, which we're not going to dwell on too much, but I tell you sort of for interest's sake. That of regular expressions, which possibly you've heard of. So a regular expression over sigma, it's kind of a syntactic object. It itself is a string with symbols like the letters and the union sign and the star. And it really corresponds to a syntactic representation of these kind of deductions with the star rule and the union rule and the concatenation rule. The concatenation rule is kind of not shown, like you kind of just, like in multiplication, you don't write the dot. Okay, so this corresponds to the deduced language. So if you look at it, it's like saying, what is this first piece? This is the single letter language A. This is the single letter language A. This is the language of all one letter strings, A or B. And then if you star it, that's the language of all strings. And so this is 2 concatenation, so it's like all the strings of the form A, then any string, then another A. So this is all the strings of length at least 2 that start with A and end with A. And this is all the strings of length at least 2 that start and end with B. This is A, this is B. So this whole thing kind of stands for the regular language, all strings that start and end with the same character. Regular expressions are kind of nice because, if you get used to playing around with them, then you look at this and you're like, oh yeah, that's all the strings that start and end with the same with the same letter. You can write it down, and that tells you that it's a regular language. And conversely, every regular language can sort of be written with a regular expression. That's the theorem, that's the tricky theorem that we didn't prove. So it's quite nice. In fact, it's, this comes up a lot in regular old computing practice. Like it's used in string searching like grep. And in practice, they have some additional features or twists, but they don't extend the concept. It's still all about regular languages. Sometimes you write bar instead of union, and sometimes R plus means R star. So that's like at least one copy of R, etc. So it's a few more like bonus deduction rules in some sense, or bonus symbols that you can use, but it still corresponds just to regular languages. Okay, so that's like a nice example of DFAs, coming up in real computer science. Any questions about regular expressions? Okay. All right, so I want to spend the last bunch of time talking a little bit more about this string searching problem. This is a bit more like stories. We're not going to really prove much. I'm not going to tell you any details, but I want to tell you this story about string searching because it's another example of what DFAs are good for. As we saw, they're kind of in some sense a wimpy model of computation, but they have their useful aspects too. So let's talk about the string searching problem. And it's a problem, just like the computational problems that we talked about at the beginning of lecture. And the simplest version of the problem is a decision problem that looks like this. The instance is I'll call it a text. It's really just a big string, but so that we don't get confused, I'll call it a text T. You should think of it as having length n, where n is really long, like 1,000,000 or 100,000 or 10 million. So that's the text you're searching. And W means the substring you're searching for. Okay? So it's a shorter string. We'll call it length k. Think of k as like 100, 1,000, or 10. And it's the most basic problem. It's the solution is yes or no. It's a decision problem. Does W occur as a substring somewhere in T? Could somebody quickly describe like literally the most naive possible algorithm for this? What was the? Yeah, you might call it linear search. It's really just like, okay, here's your input T. It's got n characters. And then you just go through all the length k substrings. In this picture, k is 3. You go through all the length k substrings and you check like, okay, is this W? Is this W? Is this W? And you might think this is a bit too naive, but sometimes you really kind of have to check this, right? Because especially if there are not too many characters, like there could be overlaps between words and stuff. So, to make sure you really get it right, you might want to do this. Okay, just check every single substring of length k to see if it's W. Now, we haven't talked much about running time and algorithmic time analysis yet. We're going to do that in not too long from now. But, informally or briefly, an algorithm that implements this, it's going to run in about n times k steps. Because there's almost n, there's like n minus k, but there's basically n different starting positions. And every time you check one of these boxes, you've got to check a length k string to see if it equals W. So roughly speaking, you're doing a k steps n many times. So that's that. And you might wonder if you could do it a little bit smarter than this. Maybe use, if it has all different letters, maybe you could just check the first k and then the next k, or try to be smarter about it. Because this is a bit of annoying. If n is, 100,000 and k is 1,000, And this is 100 million steps, which is kind of a lot. Now here's where DFAs enter the picture. And this is pretty cool. There's a different kind of algorithm that uses automata. And it's based on the following idea. What are we trying to check? We're trying to check if the string is of the form any old string, followed by W, followed by any old string. You know, the regular expression for that is like sigma star, meaning any string, then W, then sigma star. And that's a regular language. You know, that's a regular expression right there, if W is a fixed string. So for each fixed string W, like 1101, this is a regular language, which means there's some DFA that decides it. The DFA is based on W, of course. So there's some DFA M sub W that decides it. Now suppose you've got your hands on this DFA M sub W, which correctly checks if a big text contains W. And you feed T into it, and you know, how long is it going to take? It's going to take about time n, right? Because, you know, it processes each character one by one, and you like jump to another little state. So if you're writing, let's say, a DFA simulator or something, it would take only proportional to n steps, which is a lot better than n times k steps. You know, if k, the text that you're searching for, is length 100 or length 1,000, you just sped up the computation by a factor of 100 or 1,000. So that's pretty cool. Now, there's one aspect of this that's a bit cheating, or like, it might make you a little suspicious. I kind of ignored an aspect of the complexity of the problem. Can somebody suggest what it is? Yeah? Sure. Or you can go. Go ahead.
How much space the DFA takes up?
How much space the DFA takes up? Yeah, that's related to what I had in mind. Quite related. You want to say?
Matching the substring with itself.
Pardon me?
Matching the substring with itself.
Matching the substring with itself. I'm not sure I see the problem. What do you mean?
When you're doing more spread, you need to match it with itself, so the runtime should be n plus k instead.
I didn't really understand the first part of what you said, but you said the runtime would be more than n. It's true that I'm kind of ignoring something that could cost you in the runtime and also the space. Yeah, you want to?
You're ignoring the time to design and create the DFA.
Yeah, that's right. Was that what you were going to say? What were you going to say? Oh, same thing. Okay. Yeah, I mean, I think this is what you were getting at. Yeah, you have a.
Wait, if you just use a DFA, you're basically going character by character, right?
Yeah, if you use a DFA, it would go kind of character by character.
Is that the standard way of doing it?
Well, see, the naive algorithm I talked about before, where you kind of look at each k block, actually, even that can't really be implemented by a DFA, because in some sense it kind of involves looking, like here, the naive algorithm starts by looking at A1, A2, A3, which a DFA can do. But then if you think that the next step of the naive algorithm, which you might write in Python or something, looks at A2, A3, A4, it kind of needs to go back to see what A2 was again. And you know, DFAs kind of can't go back. So on the other hand, there is a DFA that, for a fixed W, that will do this check to see if W is in there. But it won't quite work like this. So you might want to think about it. In any case, what I did have in mind is this issue that, you know, here I kind of imagined, you know, if W is sort of part of the input, it's like some 10-character string or 100-character string that you're searching for. If you had this DFA, M sub W, which could check whether a string contains W, that'd be great, but, you know, you got to get it. Now, if you actually had many texts, and you were always going to search for W, then maybe you wouldn't worry too much. Sort of, it's a one-time cost to build this DFA, and then you could use it to search many texts. But you know, if you're just, that's not the most usual situation. Usually this is like all a one-time thing. You have one text and one string W that you're searching for. So you really should account for this. Now, it's not a trivial problem to like take W and build the DFA M sub W, which decides this language. But you guys could do it, I think. I think if I send you home and asked you to do it, you'd come up with an algorithm that built this DFA. I think the most straightforward way to do it uses about k cubed running time. And that's okay, but if k is 10, maybe that's okay. But if k, the length of the pattern you're searching for, is 1,000, then suddenly this is a billion steps just to make this DFA, which probably makes the whole plan pointless, especially if the length of the text is a lot less than a billion. So it's a good idea, but it's only like a really, really good idea if you could somehow make this step more efficient. So this is a nice problem that they thought about in the olden days of computer science, like the 70s. And there's three famous computer scientists, Knuth, Morris, and Pratt, that thought a lot about this problem. And they came up with a very cool, complicated solution. But the cool thing about it is they showed that you could do this step, building the automaton, much more efficiently. I don't want to get into it too much, but the number of steps in their algorithm for taking the pattern W and building the automaton M sub W is proportional to k. And that was pretty cool, because then the whole string searching problem you could do in time about k, or proportional to k to make the automaton, and then proportional to n to feed the text into the automaton. So that's really good. If n is 1,000,000 and k is 1,000, then the whole thing is like 1,000,000 and 1,000 steps. Okay, as opposed to the naive solution, which is like 1,000,000 times 1,000 steps. Okay, so this Don Knuth and Jim Morris and Von Pratt, all famous fellows. This one is actually from Pittsburgh. He was a CMU undergrad, just like you. Now he's a CMU professor. He's around. If you see him in the halls, you can give him a high five for inventing this cool algorithm. Okay, so in the last few minutes, I want to tell you a little bit about extensions of DFAs. We even talked about one at the beginning. There was the idea of maybe you could add some randomness or probability to DFAs. Or maybe DFAs where a state could have more than one arrow for each symbol coming out of it. Well, it's a funny story. DFAs were actually first studied in the 40s, not by computer scientists, but by neurophysiologists. I guess trying to model really simple brains of animals or whatnot. These two people, McCulloch and Pitts. And then, it's a pretty cool and fun idea. So it was taken up by mathematicians and linguists and electrical engineers, computer scientists in the 40s and 50s. It was really formally codified in 1959, and literally all the stuff that we talked about, except for the string searching in this lecture, came from this 1959 work by Michael Rabin and Dana Scott, two more heroes of computer science. There they are, Rabin and Scott. Scott is, well, he's a retired professor at CMU, so you may occasionally see him in the halls. You can also high-five him. And in fact, they studied these extensions of DFAs too. In fact, just like these kind of DFAs that have more than one arrow coming out that you will study on your homework, these DFAs with some magical superpowers. And actually, one thing they showed was that these magical superpowers, which seem to make DFAs much more powerful, actually don't make them more powerful. Any DFA with the magical superpower that you'll see on the homework can be simulated by just a good old normal DFA. So it's kind of cool. It shows that there's a range of different kinds of DFAs, but these kinds all have the same power in terms of what problems they can solve. And for this, they won the Turing Award, which is like the Nobel Prize for computer science. Actually, there's a lot of CMU people that have won this Turing Award. There they all are. There's like a dozen of them. Yeah, it's pretty cool. Some more heroes of computer science. There's some even more powerful DFAs, like, I just say these names for like jokes, like non-deterministic push-down automata, which decide context-free languages, and linear bounded automata, and even further version, they decide something called context-sensitive languages. There's a further generalization called Turing machines. And the name of the languages that they decide is decidable languages. Kind of funny. And this is exactly what we'll talk about in the next lecture, Turing machines, which are kind of our general model of computation.